any question about textbook, but as I said, we continue the same textbook. Doesn't correspond completely, sorry, but that's it. Okay. Rather strange. After first lecture with many students, now okay. So today's topic is topology of the space Rn. So last time we discussed algebraic properties of the space Rn, and now we start with properties related to main definition for mathematical analysis, namely limit. So I'll start with general definition of a linear normed space. So a linear space, let's say E, is called normed if there exists a function which is denoted by those two vertical lines from each side. It acts from E to R such that first, for arbitrary x in E, we have norm of x. Okay, if we are talking about linear space, I'll put arrows to indicate these are vectors. Norm of a vector is non-negative, and norm is equal to 0 if and only if x is a 0 vector of the space E. So I indicate by arrow this is a 0 vector. Second property, for arbitrary x in E and for arbitrary alpha in R, real number, we have norm of alpha x equals to modulo alpha times norm x. And third property, for arbitrary two vectors x, y in E, we have triangle inequality, norm of x plus y equals to less or equal norm of x plus norm of y. So these are main properties of arbitrary norm in a normed linear space. And first theorem, theorem 1, says that an arbitrary Euclidean space is a normed linear space with norm given by this equality, square root of the inner product of x by itself. And we say the norm is induced by the inner product. So there is a connection between analytic property, namely norm is an analytic property, and more or less algebraic properties, because inner product was an algebraic operation. Okay, proof. So I'll start with the first property, and in fact together with the first property also correctness follows from the same. So correctness of the definition of the norm and 1 follow from first property of an inner product. So let me recall, what is this first property of an inner product? Recall, what is property? Inner product is always non-negative. That was a property of arbitrary inner product. Now look, this is always non-negative, hence we can find square root, right? That is why I said correctness. So the definition is correct. Indeed, this square root is always defined. So this number is defined. Okay, first property, non-negativeness, follows immediately from properties of square root, right? Square root is always non-negative by definition from a positive, non-negative real number. And what is about this? So look, norm x equals to 0. So by definition follows that inner product of x by itself equals to 0. And then once again we apply the first property of an inner product. So if inner product equals to 0, then the element is 0. So x is 0 element. So the first property of the norm is okay. Now look at the second. So once again we substitute into the definition. So square root of alpha x times alpha x. And remember properties of the inner product. So we can put scalar before the sign of the inner product, right? So I write square root alpha times x alpha x, that is second or third property of the inner product, right? Third property. Then second property allows to change the order. So alpha x x, second property, right? Once again, third property, put alpha outside. Alpha squared times x x. And after that, remember, for arbitrary real alpha, square root of alpha squared equals to modulo alpha, right? So we obtain modulo alpha times square root of x x, and that is precisely modulo alpha times norm of x. So what we wanted. Okay, the last is third property. And we'll consider square of a norm, because this is more convenient, right? Look, what is the square of this norm? By the definition, norm is square root, hence we have no square root, but just the product, this product, right? That is x plus y times x plus y itself. Okay, now let us consider what is it by third property of the inner product. We have sum here, so x plus y plus y times x plus y. Then change the order, second property of the inner product, x plus y x plus x plus y y equals to, once again, apply third property, so x x plus y x plus x y plus y y. Once again, applying second property, we have, and also definition of the norm, we have norm x squared plus 2 times inner product x times y plus norm y squared. Now apply Cauchy-Bunyakovsky-Schwarz inequality. Cauchy-Bunyakovsky-Schwarz inequality. So we know that even modulus is less or equal than square root of product of inner products. And if modulus is bounded from bounded above, then the number itself is also bounded above by the same number, right? Because real number less or equal than its modulus, right? So we can rewrite like that: 2 times square root x x times y y but that is norm of x, that is norm of y, right? Square root. So what is it? Norm x squared plus 2 times norm x times norm y plus norm y squared, and that is precisely square of the sum norm x plus norm y. Since both terms, I mean the left-hand side and the right-hand side, not those, but left-hand side of what we want are non-negative, right? Then if squares are estimated by this way, then also we have the inequality for those values themselves, right? And that's all. Okay. Corollary. We know very important example of a Euclidean space, right? Sorry, here space. So as a corollary, we obtain that Rn is a linear normed linear space, a normed linear space. Also, let me make a remark, or maybe maybe I'll write it here, just in this corollary. In particular, norm of x plus y less or equal norm of x plus norm of y, I mean triangle inequality, means what it means. Look. So recall, what is inner product in Rn? Inner product in Rn, if x is x1 so on xn, y is y1 so on yn, then inner product was defined as such a sum, xi times yi, right? That is the definition of the inner product in Rn. And now look, what is norm? Norm, square root of inner product by itself, right? So we obtain that norm in Rn is given by this expression, square root of this sum, right? And then what is this inequality? Let me write it. So we can write like that, square root of the sum xi plus yi squared. Once again, I'll put modulus here, less or equal sum square root xi modulus squared plus square root of the sum modulo yi squared. That is a corollary of in fact of general triangle inequality, right? So we have triangle inequality for an arbitrary Euclidean space. And in particular for Rn, this triangle equality reads like this inequality, and that is called Minkowski inequality. And also remark if a space E is a complex linear space, then there is only one change in the definition of a complex linear normed space. So what is this difference? Look, the first one same, the last one same, and the second one, the only difference is here. So for arbitrary second property will be like that. For arbitrary alpha now in C, we have norm of alpha x equals to modulo alpha times norm of x. Everything else is absolutely the same. Now look. So instead of theorem 1, that is continuation of this remark, theorem 1 has an analog for an arbitrary complex Euclidean space, also called, let me recall, unitary space. And look what we need to change. In the formulation, nothing, right? Except for, unitary space, normed linear complex space, right? And what is in the proof? Look, where we'll need to change something. Yeah, proof should be modified. So changes in the proof. What should be changed? Look, here, second property is different for unitary spaces, right? Because, look, for real, we could change the order without anything else, right? Equal. And for complex, we need to put conjugate, right? But what will be different after that? So for second, look, square root alpha times x alpha x, right? Then we write like that, alpha times, if we change, we put conjugate. conjugate, right? After that, we can take alpha outside, but with conjugate. So we have alpha times alpha conjugate times xx conjugate. But we know, even for unitary space, this guy is real non-negative. And if it is real, forget about this conjugate, right? And what is it? Modulo alpha squared. So once again, we obtain modulo alpha times norm of x, right? So you see, the only change for the proof of second property is here. Now for the third property. Once again, when we use second, change here, right? Yeah. So for the third, look where we'll need to make a change. We have x plus y plus y x plus y equals to, when we change the order, we need to put conjugate. X plus y x conjugate plus x plus y y also conjugate. That is, once again, x conjugate plus y x conjugate plus x y conjugate plus y conjugate. Now, the first and the last terms, they are real, non-negative. So may forget about conjugate, right? And here we change back, forget about conjugate again. So we have norm x squared plus xy plus xy conjugate plus norm y squared. Okay, now we have a complex number plus conjugate to the same number. What is it? 2 times real part. That is norm x squared plus 2 real part of this inner product plus norm y squared. But real part of a complex number is less or equal than modulus of this complex number, right? So we write once again norm x squared plus 2 modulus of this inner product or scalar product, and then finally we can apply once again Cauchy-Bunyakovsky fact, right? So, and it means that as a corollary, Cn is a normed complex linear space, right? And in particular, Minkowski inequality holds not only for real x and y, right? But also for complex as well. And you see here in this inequality, nothing about spaces and so on. That is just an inequality for numbers. And this inequality is valid not only for real numbers but also for complex numbers, right? As we checked. Okay, that is about Minkowski inequality. And last remark is about R2 and R3. R3, R2. What happens then? So norm of x, what is it? You know vectors on plane and in the space, right? Length of vector, right? That is precisely length of vector. So length of a vector, right? Which you studied in school, right? So, and that is, you see, indeed, that is triangle inequality, right? One side of a triangle less or equal than the sum of two sides. So, familiar. That is why it is indeed triangle inequality. Okay, so now let me go further. So, in fact, what I want to do now, you see, I want to explain the word topology. And the best way to do it is to go more and more abstract spaces, but we'll look only for Rn. So it means definitions are very general, but we don't consider anything very abstract. We look only at Rn, nothing else. I mentioned Cn, but once again, I don't plan to work with them, at least now. Okay, so now we go to the next general definition. A metric space. A metric space X rho is a set X with given function rho from Cartesian product x to x to r, which satisfy the following properties. First, for arbitrary x, y in X, we have rho of x, y is non-negative, and rho of x, y equals to 0 if and only if x equals to y. Second, for arbitrary x and y in X, rho of X y equals to rho of y x. Third, triangle inequality again. For arbitrary x, y, z in X, we have rho of x, y less or equal rho of x, z plus rho of z, y. So rho is called rho of x, y is called the distance between x and y. So in the end, why did we only consider the real part of the complex n x, y? No, real part was of the inner product x, y. And it was xy plus xy conjugate. And that is 2 times real part, right? So that is why. Okay. А там других вопросов не было? Тут я что-то не смотрел. Ну, самый первый про книжку, это в самом начале было. Okay. So, let me compare 2 very general definitions. The first one was about normed linear space, right? So, look, for normed linear space, we introduced norm. Norm is a kind of length, right? It was a generalization of the length. So, how to measure distance, right? So, look, for normed linear space, we want to measure distance, right? But simultaneously, we use also other structures like inner product, sum of vectors, and so on. So we use a lot of algebraic structure. Now it turns out, for mathematical analysis, you don't need, in many places, you don't need any algebraic structure. Look, metric space. Nothing, just X is a set. Doesn't matter, no algebraic properties. You don't suppose anything, right? Nothing said about X. The only thing, you need somehow to measure distance between elements of this set. And once again, you see, just distance is 0 only if elements coincide, right? Otherwise, in any case, it is non-negative. Of course, it is symmetric, doesn't matter in which direction you measure the distance, right? And triangle inequality. So once again, that is completely abstract. Just 3 points, distance between 2 of them less or equal than sum of distances from one to another and from the second to another, right? So very abstract thing. But even this is too much to define limit, because you see there are numbers, right? There are numbers, and you will see that topology to introduce topology. You don't need even numbers. Nothing. Okay, we'll continue after the break. Okay, so now theorem 2, an arbitrary complex but not necessarily complex linear normed space is a metric space with the distance given by x, okay, normed space E, x y rho of xy equals to norm of the difference x minus y. And we say the distance or metric distance is induced by the norm. Like before, you see, norm may be induced by in the product, and metric may be induced by the norm. Proof. Here practically nothing to prove. Look, everything is just particular cases. So norm is always non-negative, we know, right? So it means first property is immediate, right? Also, if norm equals to 0, then the element is 0. And what means difference is 0? Means x equals to y, right? So first property is obvious. Then the second property follows from norm of x minus y equals to norm of y minus x, right? Because what is difference? What is the difference between those two elements? Minus times, right? And remember property of norm. You see. So why it is? Because norm of y minus x we can rewrite like norm of minus x minus y, right? And that is minus 1. Minus 1 gives modulo minus 1 times norm of x minus y. By second property of the norm, modulo of minus 1 is 1. So norm of x minus y. And that is precisely second property, symmetry. And the last, third property, okay, we can write like that, rho of xy, then I will write x minus z plus z minus y, right? So we add and subtract one vector, z, and after that we apply triangle inequality for the norm. Which gives immediately the triangle inequality for the distance, right? That's it. Okay. And from now on, I plan to give a lot of definitions. Part of them were given before for real numbers, like neighborhood, and now I'll introduce a neighborhood in a more general situation. In fact, all definitions will be given for an arbitrary metric space. Yeah? I said it's immediate, you see. Norm of x minus y is always non-negative, right? And norm equals to 0 means x equals to y. So I didn't write here because they are almost immediate. Okay, so now a long series of definitions. All definitions are given for general case of a metric space, but to better understand, just imagine R2 plane. That is the best way. Just look, hold in your mind the plane. That's the best. Although some words even from R3, from the space, are taken. For example, the first definition, an open ball with center at x0, once again, metric space, everything in metric space, so I'll indicate here this metric space, x, and of radius epsilon greater than 0, and that is the same as epsilon neighborhood. Of x0 is the following set. So that is all points x such that the distance from x0 to x less than epsilon. It is open ball. And notation, okay, sometimes to indicate ball, letter B is used, but since that is neighborhood, so I'll use u epsilon of x0. Yeah. That is epsilon neighborhood. Okay? Okay, so yeah, and then very long series, as I said, definitions. So, question? Okay. x0 is an inner point of, okay, how the set is denoted, let it be E. E in X if there exists an epsilon neighborhood, so epsilon greater than 0, such that u epsilon of x0 is an E. So every point belongs to this set together with a neighborhood. Okay, next, interior. Interior of a set X is the set of all inner points of E. Notations interior, E interior, and also quite often it is denoted by E with a small circle over E. That is also a notation for interior, Also, next definition, if all points of E are its inner points, then E is called an open set. An open set. In other words, it means that we have all points of E are inner points, so E is included into interior of E, right? And also, that is a little bit strange from the first glance, but we say empty set is open. I mean, you can say why I added it, because rigorously speaking, look, all points are in inner points, right? That is true, because we have no points. So all points are everything, inner and what you want, right? Because you have no points. But nevertheless, it's better to say explicitly. So empty set is open. Okay. Then next definition. X naught is an adherent point of E in X if for any epsilon greater than 0, u epsilon of X naught intersected with E is not empty. So there exists at least one point of the set E in an arbitrary neighborhood. Okay, next definition. The set of all adherent points of E is called the closure of E. Notation closure, or quite often like complex conjugate, the same bar is used to indicate closure. Then next definition, E if E contains all its adherent points, then E is called a closed set. So it means by definition, closure is a subset of E, right? So all points of closure are Good question to discuss it. What is the difference between normed linear space and the metric space? Once again, for a metric space, you have a set where you have nothing. No sum, no multiplication by a number, nothing. You don't need to suppose anything for a metric space. Yeah? Yeah, the only thing is to get those properties, nothing else. Okay. Yeah, once again, empty set is closed. Why? Because, look, if you take as E an empty set, right? Then you have here empty set always, right? It means empty set has no adherent points, right? So it means closure is empty. Empty set is a subset of empty set, right? That is why, indeed, empty set is closed. Okay, now lemma 1. So we have for arbitrary set E, we have opposite inclusions. So interior is always a part of a set, and the set is always a part of its clause. Proof. Look, so what is in the point? If there is epsilon greater than 0 such that a neighborhood belongs to the set, right? But look at the definition of a neighborhood. The point x naught is definitely in the neighborhood, right? Because distance rho x naught is 0, right? And 0 less than epsilon. So arbitrary epsilon neighborhood contains the point x naught itself, right? And it means that if you have an inner point, then this point is automatically a point of the set itself, right? For sure. That is written here. And from the same point of view, what is about that inclusion? Look, if x naught is a point of our set E, right? Then what happens? Once again, arbitrary epsilon neighborhood of this set, of this point, right, has non-empty intersection because the point x naught itself is in this intersection, right? Because arbitrary neighborhood contains the point x naught, right? And if we suppose x naught is an E, right, then for sure this intersection not empty, right? It means any point of our set E is automatically an adherent point of this set. Maybe there are some other points. Okay. Yeah. Empty set is closed. Why empty set is closed? Here? Yeah. For an empty set. It means no adherent points. Empty set has no adherent points, right? Because this is always empty. No adherent points. Okay. So proof I gave. And as a corollary, because of the definitions, look. So corollary. So we know open set if this inclusion holds, right? For arbitrary set, interior is a part of it. So E is open if and only if interior E coincide with E. And similar definition of closed set. Where is it? Yeah. Definition. Closure is a part of E. For arbitrary, E is a part of clause. So if we have closed set, then we have equality. E is closed if and only if closure of E coincide with E. It's quite often you can find books where these are definitions. So it's not important what you choose as a definition. That one. Next lemma, lemma 2. If E1 is a subset of E2, then interior of E1 is a subset of interior of E2, and closure of E1 is a subset of closure of E2. Proof. So look, suppose X naught belongs to interior of E1. What it means? It means by the definition there exists epsilon greater than 0 such that U epsilon of X naught is included into E1. So interior means you have a neighborhood which is inside our set. But E1 is a part of E2, right? So it means we have a neighborhood which is a part of E2. And it means that X naught is an interior of E2 as well. And that means this inclusion. Okay, second. So suppose X naught is a point in the closure. Then what it means? It means that for arbitrary epsilon greater than 0, the intersection with E1 is non-empty, right? Intersection with smaller set is non-empty, right? Then for sure intersection with larger set is also non-empty, right? So we obtain that intersection with a larger set is non-empty as well. And it means that X naught is a point of closure of E2. That's it. Okay. Next property is looks a little bit strange because an open ball in a metric space is an open set. You can say, but it is called open, right? It doesn't matter. Maybe it was bad title, right? And in fact, open ball maybe not an open set, right? That is an assertion which should be proved. So, proof. And now the best thing is to draw a picture. So what we want to do, we have an open ball. Let me draw it like a disk, right? So consider an open ball u epsilon of x naught. So it means here we have x naught, and that is epsilon, right? If we, as I said, always imagine R2 in your mind. We want to prove that it's an open set. What it means? Take arbitrary point, let it be x in our open ball. So somewhere here we take a point x, right? Somewhere here we take a point x. And we want to prove that is an inner point, right? So to prove that something is open, we need to prove that arbitrary point is an inner point. Inner means this belongs to our set together with a neighborhood. So it means we need to prove there is a smaller maybe neighborhood, right? Which is inside our given open ball, right? And geometrically it's obvious, right? If we have x, then for sure that is okay. I draw a picture. But of course we need to realize this picture, to describe it in terms of our metric, our distance, right? And what is about this distance? Which distance we can take here? Look, geometrically means that one, right? This distance is okay. And what is that distance geometrically? Radius minus distance between x naught and x, right? And indeed, you see, as we know, so consider now an open ball with center at x and radius, which radius? Epsilon minus distance between x naught and x, right? That is what we saw from the picture. Why I can consider it? Because as we know, this distance for sure is less than epsilon, right? That is because x in this ball. So by definition, what is this ball? The only definition, the distance is less than epsilon. So it means this number is positive. And we can consider such an open ball, right? That is an open ball. Now, for arbitrary point y in this ball, what can we say? So I took arbitrary point y inside this smaller ball, right? Then what happens? We can write the following chain of inequalities. Distance from y to x naught, So I want to prove that in fact this point y belongs to our original ball, right? So what is difference from from y to x naught? We can use triangle inequality. I can insert arbitrary third point, and of course I'll took that one, x. So less or equal by the triangle inequality rho of yx plus rho of xy. Sorry, x naught, right? That is triangle inequality. Now, what can we say about this distance? We know y is a point of our open ball. By the definition of the open ball, that is strictly less, this distance strictly less than what? Than the radius, right? And radius was epsilon minus rho of x naught x. And that one I add as it was here. And you see now what happens. Cancel, that is epsilon, right? So we obtain distance from y to x naught strictly less than epsilon. It means that what we proved. Hence, our open neighborhood, our neighborhood of the point x is a subset of our original open ball. So we took arbitrary point of our open ball, and indeed that point belongs to this ball together with its neighborhood. Yeah? Take arbitrary point, belongs together with the neighborhood. That's it. So we have proved. Okay, next definition is again game of words once again. So definition: a closed ball with center at x naught in x and radius epsilon greater than 0 is the following. We'll denote it by, okay, let it be b epsilon x naught closed. Remember, bar is for closure, right? Where is it? Yeah, bar is for closure. But be careful, in fact, that is just a notation. So what is it? That is the set of all points such that distance between x naught and x is less or equal than epsilon. That is a closed ball. And of course, we should check if indeed, and that is just now time to prove. Oops. That is lemma 4. Lemma 4. For arbitrary epsilon greater than 0 and for arbitrary x naught in x, closed ball is a closed set. So once again, like before, we need to check if that word was chosen correctly. So proof. Let x be an adherent point of b epsilon x naught bar. What it means? It means that for arbitrary eta greater than 0, we have the intersection of neighborhood, eta neighborhood of x, together with our set, that one, is not empty. Not empty, right? So, look, I look just at the definition. So, what is closed set? If E contains all its adherent points. So, it means what I need to check. I need to take arbitrary adherent point, and adherent point means, once again, what is adherent point? For arbitrary, now I cannot use same letter, right? I need to use another one. Intersection should be non-empty. Okay, what it means? It means, yeah, what is this intersection? So, there exists Z which belongs to this intersection. And what it means? That belongs to this intersection. It means that we have two inequalities. Rho of x to z is less than eta, strictly less, right? And also rho of x naught to z is strictly less than epsilon. Oh, not strictly, less or equal, right? Less or equal than epsilon. So then from triangle inequality we have the distance from x to x naught is less or equal than distance from x to z plus rho of z to x naught, and that is strictly less than epsilon plus eta, right? Now, let me write down what we obtained. So, for arbitrary eta greater than 0, we have a number, distance from x to x naught, is strictly less than epsilon plus eta. Look, we have a real number, fixed, right? But it is strictly less than epsilon plus eta for arbitrary eta greater than 0. Then what follows? It follows that this number is less or equal than epsilon, right? Because if it would be strictly greater, then this inequality is impossible for sufficiently small eta, right? And what it means? It means that x belongs to our closed ball. So we took arbitrary adherent point, and it belongs to the set itself. It means that the closed ball is indeed closed set. So word was chosen correctly. Okay, I think, yeah, now we should stop because next theorem is, yeah, a lot of lemmas, and I'll start next lecture with a theorem. Okay, that's all for today. Thanks for your attention. Oh, sorry, there is a question. Explain more about lemma 2 from previous lecture. R2n has a complex structure given by multiplication. The only thing which you need to understand about lemma 2 from previous lecture is that square of that matrix, block matrix, is minus unit matrix. That's all. Just multiply the matrix by itself. Okay.